Hi, let's solve some more previous year gate problems from the chapter bending of beams. Okay, so a cantilever beam OP is connected to another beam PQ with a pin joint as shown in the figure. So this is a pin joint, this is a hinge. A load of 10 kilonewton is applied at the midpoint of PQ. The magnitude of bending moment in kilonewton meter at fixed end. O you have to find. Okay, so first of all, at this hinge bending moment is always 0. Okay, and due to this hinge these two beams OP and PQ can be analyzed separately. Okay, like this. This is O, this is P, and this is P, this is Q point. There will be a reaction at point Q, let it be RQ, and there will be a reaction at point P, let it be RP, in the beam PQ. Okay, but this reaction RP will be equal to the reaction the reaction at P in the beam OP also. Okay, so this reaction and this reaction will be equal, but they will be acting in the opposite direction. Okay, and the point, another point is that bending moment at this hinge is 0. Okay, so there is one more load, that is 10 kilonewton. So analyze beam PQ. What we get, that RP plus RQ is equal to 10 kilonewton, and at this hinge the moment will be 0. So sigma moment at moment at P, will be 0. So this gives me RQ is equal to 5 kilonewton, and which gives me RP is equal to 5 kilonewton. Okay, now when I get RP is equal to 5 kilonewton here, the magnitude of reaction at point P in the beam OP will also be same, and this will be 5 kilonewton. Okay, now you know the distance from O, which is 2 meter. We can find the bending moment at the fixed end, which is 5 kilonewton into 2 meters, that is 10 kilonewton meter, and we have to give the answer in kilonewton meter. Okay, next question. A cantilever beam with cross section of 6 mm side is subjected to a load of 2 kilonewton normal to the top surface as shown in the figure. The Young's modulus of elasticity of the material of the beam is 210 gigapascal. Okay, so this is E. The magnitude of slope in radians at Q is, and Q is 20 mm from the fixed end. Okay, so let's analyze the cross section at Q directly. Okay, what are the forces and moments that will be present at the cross section Q? So there will be a vertical downward force at Q, okay, which is 2 kilonewton, and due to this 2 kilonewton force there will be a moment at cross section Q also, and the value of that moment will be, this distance is 80 mm. Okay, so 2 into 10 raised to power 3, which is load 2000 newton, into 0.08 meter. So this will be the value of moment in Newton meter. Okay, so this will be, I guess, 160 Newton meter. Okay, so at point Q there will be a load plus there will be a moment due to this 2 kilonewton load, okay, whose value is 160 Newton meter. Now all we can do is we can apply superposition method. The value of slope at the free end in a cantilever beam, okay, by a load acting at the free end is given by PL square by 2EI, where P is the value of the load, L is the length of the beam, which is in this case 0.02 meters. Okay, and E is 210 gigapascal. I, moment of inertia. What is the moment of inertia of this beam? Side is given, the cross section is square, so it will be a raised to the power 4 by 12, where a is 6 mm, that is 0.006 meter raised to the power 4 upon 12. So this will be I. Okay, this I have written the slope due to the load acting at the free end, plus there will be slope due to this moment also, and in the same direction. Okay, so the value of slope when a moment is acting at the free end is given by ml by ei. Okay, m is 160 newton meter. Here we have found out. L we know, E we know, I we know. Okay, so now put the values. 2 into 10 to the power 3 into 0.02 square upon 2 into 210 into 10 to the power 9 into 0.006 raised to the power 4 upon 12 plus 160 Newton meter into 0.02 meters upon 210 into 10 to the power 9 into I, that is 0.006 raised to the power 4 by 12. You can take EI common or whatever you want. So theta will be 0.0176 plus 0.1410. Okay, this is the value, and the sum will be equal to 0.158 radian. Okay, so theta will be in radian, that is 0.158. 0.158. Okay, so this is the answer. So wherever you have to find the slope or deflection, just analyze that cross section. Okay, and you will get your answer. Next problem is, it's a pretty simple problem. The value of moment of inertia of the section shown in the figure about the x-axis. Okay, so the axis is, there is a problem in this figure. It's not correctly drawn. This is in the center. Okay, these squares that are cut out, these are in the center, and this is the x-axis. Okay, x. Okay, so all you have to do is find the moment of inertia of 1, find the moment of inertia of 2 about this x-axis, and then subtract these two moment of inertias from figure 3. Okay, so let's find the moment of inertia of square 1 about its CG. Okay, and which is equal to a raised to the power 4 upon 12, because it is square, so it will be equal to a raised to the power 4 by 12, where a is the side of the square. Okay, so a is 30 raised to the power 4 upon 12. So this is the moment of inertia about its own CG. Now you have to find the moment of inertia of first figure about this x-axis. So we can apply the parallel axis theorem. Okay, which states that Ixx1 is equal to ICG plus AH square. Okay, ICG is 30 raised to the power 4 upon 12, which we have found out, plus A is area of the square, which is 30 square, and H is the distance of the CG of the square from the x-axis. So this is 15, this is 45, this is 30, this also becomes 15. So H is 30. Okay, square. So this becomes 30 raised to the power 4 upon 12 plus 30 raised to the power 4. This is 30 raised to the power 4. Okay, so this is the moment of inertia of first figure about x-axis. Okay, because we have to find the moment of inertia of the figure about the x-axis. Okay, now similarly I can find the moment of inertia of second figure about x-axis, and it will be same, because the side of the square is same, the distance is same, the distance of the center of gravity of the square from the x-axis is also same, so it will be equal to Ixx1. Okay, and the moment of inertia about x-axis of the bigger figure, that is I3, this is equal to BD cube by 12. Okay, because it is a rectangle, so BD cube by 12. So this will be B, because we have to find the moment of inertia about x axis. So 60 is parallel to x axis, so this will be B, and the other side will be D. Okay, so B is 60, D is 120 cube by 12. Okay, and this will be about the axis which is passing through its CG. Okay, so now the moment of inertia of the figure, which is represented by Ixx here, is equal to I3 minus twice of Ixx1. Okay, so I3 is 60 into 120 cube by 12 minus twice of 30 raised to the power 4 by 12 plus 30 raised to the power 4. Okay, so the value will be 8640000 minus 2 into 8775000. No, it's 8775000. Yeah, be careful while solving. Okay, don't commit any calculation error. So this gives me 6885000, and that will be 6.885 into 10 raised to the power 6 mm raised to the power 4. Okay, because we are working in mm only. So 6.885, that is option B is our answer. Okay, next question. For the overhanging beam shown in figure, the magnitude of maximum bending moment in kilonewton meter is. Okay, try to solve these type of questions by drawing the bending moment diagram, because you will see a clear picture when you have the bending moment diagram of the given figure in front of you. Okay, so let the reaction at point A is RA, and let the reaction at point B is RB. Okay, so I can find the reactions at RA and RB. Simple. The sum of moments at point A is 0. Okay, and this becomes 20 into 6. The total distance is 6 meters from 20 kilonewton load. Okay, and it is acting in the clockwise direction. Let it be positive. You can take anti-clockwise as positive, whatever be your wish. So let clockwise, the direction moment acting in clockwise direction, be positive. Okay, so 20 into 6, that is 20 kilonewton into 6 meter. Okay, minus RB into 4, because it is in the anti-clockwise direction, so it will be with a minus sign. RB into 4 is the distance from the point A. Okay, and then what about this uniformly distributed load? Whenever we find the reactions, what we assume that all of this uniformly distributed load is actually concentrated at its CG. Okay, so the total load is 10 kilonewton per meter. 10 kilonewton into 4. Okay, the total load becomes 40 kilonewton. So the total load is 40 kilonewton, and we assume that it is concentrated at its CG, and the distance of this uniformly distributed load from its the distance of CG of this uniformly distributed load from the point A is 2 meters. Okay, and it is acting in the clockwise direction, so positive 40 kilonewton into 2 meters. This is equal to 0. Okay, so this will be 120 minus 4 RB plus 80 is equal to 0. So that implies RB is equal to 50 kilonewton. Okay, we are taking the load in kilonewton, so RB is 50 kilonewton. Next is RA plus RB, that is sum of forces in y direction, is equal to 0. So RA plus RB is the total load that is acting on the beam, which is 20 plus 40, this 20 kilonewton load plus this 40 kilonewton load, so this will be 60 kilonewton, and RB is 50 kilonewton, so that implies RA is equal to 10 kilonewton. Now we have the reactions with us. Okay, so now let's draw the bending moment diagram of this given figure. Okay, This point is A, this point is B, and this is C. Okay, so let's start from right hand side. Okay, due to this load, this 20 kilonewton load, there will be hogging in the beam. Okay, and hogging, we take it with a negative sign. Okay, and up to B there is no load present in the entire beam. So can I directly say that at point B the moment will be equal to 20 into 2 meters, that is 40 kilonewton meter, obviously with a negative sign, but we have to find the magnitude, so we can ignore the negative sign. Okay, and this will be linear, okay, because point load is acting, so this will be a linear, this will be a straight line up to point B. So this is 40, this value is 40 up to at point B, 40 kilonewton meter. Okay, now after this uniformly distributed load is acting. So let me rub it. RB is 50 kilonewton. I'm writing just 50. RA is 10. Okay, so to analyze this uniformly distributed load, let's take a cross section XX at a distance of X from this point B. Okay, now write the moment equation in this part of the beam. Okay, so this will be minus 20 into 2 plus x. Minus 20 is the load, this load which is acting, and from the cross section XX the total distance of this load is 20, the total distance of this load is 2 plus x, so this is 2 plus x with a negative sign because it is causing hogging in the beam, and hogging we take it with a negative sign. Okay, then comes this reaction in the upward direction and it is causing sagging in the beam, which will be taking with positive sign, and the distance of this reaction from this XX section is x only, so this will be plus 50x. Okay, and then this comes the uniformly distributed load. Okay, so the total load, I have told you how do we find the total load. The total load will be 10 into x. Okay, because 10 kilonewton per meter. Okay, the distance is x, so the total load will be 10x up to cross section XX only. Okay, and the moment caused by this uniformly distributed load about this cross section XX is found out by assuming that all of this 10x is acting at the center of this uniformly distributed load of distance x. Okay, so this distance will be x by 2. Okay, so this is also causing hogging of beam, so minus 10x into x by 2. This will be moment at cross section XX. Okay, solve it. Minus 40 minus 20x plus 50x and minus 5x square is equal to mxx. Okay, so this is a quadratic equation. Minus 5x square plus 30x minus 40 is equal to mxx. So this is a quadratic equation, so the graph will not be linear. Okay, will not be a straight line. Now we have to find whether the whether the bending moment in this section of the beam crosses 40 kilonewton meter or not. What we can do, we can differentiate it with respect to x, because dm by dx, when dm by dx will be 0, okay, this will signify that where the bending moment is maximum. Okay, so for maximum bending moment, dm by dx is 0, and this will be minus 10x plus 30, which will be equal to 0, and x is equal to 3 meters. So in this part of section, in this part of the figure, at x is equal to 3 meters, there will be maximum bending moment. Okay, x is from point B, so at x is equal to 3 meters, here, somewhat here, you will get the maximum bending moment. Let's calculate its value by putting x is equal to 3 meter here. Okay, so that implies minus 5 3 square plus 30 into 3 minus 40 is equal to mxx. Xx is actually 3 meters. Okay, so this becomes 5 kilonewton meter. So in this part, the magnitude of maximum bending moment is 5 kilonewton meter. Okay, it's not exceeding 40 kilonewton meters. Okay, also to be further sure, what we do is we put this equation equal to 0. We'll see at what point the bending moment is actually getting 0 in this part of the figure. Okay, that we are analyzing. So when we put this quadratic equation equal to 0, that is minus 5x square plus 30x minus 40 is equal to 0, we get two values of x, which is equal to x equal to 4 meter, x is equal to 2 meters. Okay, so x is equal to 4 meters, that is at point A the bending moment will be 0. Okay, and x is equal to 2 meters, x is equal to 2 meters, somewhat here the bending moment will again be 0. So I can be sure the graph will be somewhat like this. This is not a straight line. Okay, it is a bit difficult to draw here. This is not a straight line, this is something like this. Yeah, let me draw it more carefully. Okay, because this is an important part, so it will be somewhat like this. Okay, now it's better. And at x is equal to, so this is x is equal to 2 meters, and at x is equal to 3 meters, the value of maximum bending moment is 5 kilonewton meter. Okay, and see, we have got the value with a positive sign, and we are getting the same in the bending moment diagram. Okay, so the maximum magnitude of bending moment is 40 kilonewton meter only. Okay, this will be your answer. Thank you.